Let's wrap up section 1.3 by recognizing the relationship between linear velocity and angular velocity. Definition: if v is the linear velocity, remember linear velocity is distance changing in time. If v is the linear velocity of a point on a circle of radius r, and omega is its angular velocity is change in angle with respect to time, then the relationship between the linear and angular velocity is given by, if we begin with linear velocity v, that's calculated as arc length over time. Now recall that arc length is given by alpha times r. Let me scoot to the side here. Alpha times r is arc length divided by time. Now I'm just going to rearrange this a little bit. I'm going to move the alpha over t out to the left and r to the right. It's the exact same information, just in a new perspective with our writing. Then we can recognize we have alpha over t. Alpha over t is angular velocity, and we still have that factor r there. So in short, linear velocity is equal to angular velocity times radius. So that expresses the relationship between the two types of velocity that we've studied in this section. Let's use this formula to solve a couple of problems. Example 6. What is the linear velocity in miles per hour of a point on the equator? Assume the radius of the Earth is 3,950 miles, a factor that we've used before. And then we're going to round our answer to the nearest mile per hour. So we're calculating a linear velocity for a point moving along the equator as the Earth rotates on its axis. So the relationship between linear velocity and angular velocity is v equals omega r. We're attempting to calculate linear velocity, so we need to know the angular velocity of the Earth. Well, we can think about the Earth rotating one revolution, or 2 pi radians, in 24 hours. And the radius of the Earth is 3,950 miles. Now, notice here I did not write down any units for radians. In a calculation like this, we're going to ignore radians. Radians don't bring any new information to our units, although we sometimes write those down when we're doing conversion problems. In this case, you can see that the resulting units are miles per hour. So let's type this into our calculator. We have 2 pi times 3,950 divided by 24 hours. We're going to round to the nearest tenth, so we end up with 1,034.1. 1,034.1 miles per hour. Now, because that velocity is constant, a person at the equator doesn't experience or sense the movement of 1,034 miles per hour. Once again, because it's a constant velocity. Knowing the relationship between linear and angular velocity can also come in handy or be useful when you're dealing with engineering problems, such as in example 7. It says a belt contains 2 pulleys with radii 3 inches and 5 inches as shown below. The velocity of point A on the belt is 10 feet per second. What is the linear velocity in feet per second and the angular velocity in radians per second for point B and also for point C? Now here's a good hint. Every point on the belt is moving at the same speed. And since everything is moving in the same direction, all 3 points have the same linear velocity. So the linear velocity for points A, B, and C are universally 10 feet per second. However, the angular velocity for point B and point C will be different. So let's consider point B's angular velocity. Working on point B, we're going to remember that linear velocity is equal to angular velocity times radius. If we want to find the angular velocity for point B in radians per second, then we're going to need to know the radius of the circle around which it's traveling. We can see that's 3 inches. And we know that the linear velocity is 10 feet per second. Now we have a little bit of a problem here. If I plug in 10 for V on the left, it's in feet per second, and on the other side we have inches. So we're going to have to go ahead and convert those feet to inches within our problem here. So in 1 foot there are 12 inches. Now we can see on the left the units are inches per second, and on the right side, that's going to match up with inches. Now, notice when we divide both sides here by 3 inches, everything cancels over there on the right, and notice we're dividing inches by inches. So we end up on the left, 10 times 12, or 120 divided by 3, 40. Not really any units on the top, 40 something per second. Now would be an appropriate time to recognize that though radians are unitless, we can go ahead and think of it in radians per second. So the angular velocity for point B is 40 radians per second. We can expect the angular velocity for point C to be different because it's traveling around a circle of a different radius. Since the circle that point C is moving around at the same rate that point B is moving around the smaller circle, then C is going to, or the angle is going to change slower in time than at point B. So working a similar calculation here, and I'm going to scoot over here so I can have some more room. For point C, we're going to start with the conversion between linear velocity and angular velocity. Again, the linear velocity for point C is 10 feet per second. Let's take the time to convert those feet to inches. We know in 1 foot there are 12 inches, and that will allow us to calculate omega for point C with a radius of 5 inches. On the left side, I'm going to cancel the feet, so we have inches per second. And in case this fraction was a little bit hard to understand the first time around, let me write it a little differently. Maybe that will help you to understand the operation. I'm dividing both sides by 5 inches, which is the same thing as multiplying by the reciprocal, right? So I'm multiplying by 1 over 5 inches. It's a little clearer to see when I'm not dealing with a complex fraction. Hopefully that makes it easier for you to see how those inches do in fact cancel. Then we can go ahead and multiply, and we'll obtain 120 divided by 5. 120 divided by 5 is 24, and we have again radians per second. Everything over here canceled. So the angular velocity for point C then is 24 radians per second. So again, because C is moving over a larger distance at the same rate, the angle is changing slower than it is at point B. So in this section, you learned how to set up conversion factors. You learned the difference between linear and angular velocity. And in this video, you learned the relationship between linear and angular velocity.